Okay, so last time we left off, we were talking about rational numbers, and a rational number is a fancy way of saying a fractional number, because you'll remember we defined a rational number simply as one that could be written as one integer divided by another, with the exception that, hey, you can't divide by a zero. So aside from that, dividing by zero issue, which we went over last time, why that can't happen. We also talked about mixed numbers, something like that, improper fractions, mixed numbers. I hate that term. I think it's a little bit elementary and not necessary for our purposes to really worry about that business. So let's not worry about it at all. But what we can do, an important thing that we can do, is that we can use division. We can use division to figure out what a fraction looks like if we were to want to write it as a decimal. Decimal. And so if we think about it, a fraction, just like 5 over 8, 5/8, a fraction is literally saying the top number divided by the bottom number. So when you say 5/8, you are literally saying 5 divided by 8. And it doesn't really get any more complicated than that. You got to think about division. Maybe even Tom Clancy's The Division. So what we'll do, let's figure out 5/8 together, huh? We'll do it as a big happy team together here. So 5/8 will, I'm thinking 5 being divided into 8, or rather the other way, 8 being divided into 5. Well, you can immediately see a problem if you remember kind of your old school division. 8 doesn't go into 5, does it? Because 8 is greater than 5. That's okay once we start thinking in terms of decimal points. So while 8 won't go into 5, I can introduce a decimal point. They line up above the dividend itself. This means that secretly there's a 0 here for this first, because that's like saying 8 doesn't go into 5. It goes into 5 0 times. So you can put a 0 there. And now, if you think about it, the number 5, you could, if you're bored, you could write it as 5.0000000. You can put as many zeros there as your heart desires. But what instead we're going to do is, knowing we can use as many zeros as we like, we're just going to take it one at a time. Give ourselves a new 0 if we feel the need to. So now I'm going to say that 8 is going into 50. 8 is going into 50. Now here is where having your multiplication table down pat is crucial. It's almost just vital, straight up. Because you need to know that 8 times 6 is 48. So that tells you that 8 goes into 50 6 times and creates 48. And now that you've already dealt with the decimal point, you don't have to worry about trying to put any more decimal points. You already know the basic form of the answer. So you do that. I'm going to have to be a little more judicious with my space. You got a 2. Now, does 8 go into 2? Not exactly, because it's greater than. So whatever. Give yourself another 0 here and bring that bad boy down. Not bad, not bad. So now, how many times will 8 go into 20? 2 times. So I'm going to put a 2 up here. I'm going to extend this. Put a 2 up here. And since 8 times 2 is 16, I would put a 16 down there. And here's how it's going to work. We're going to keep going until either A, we're done. We get a 0 remainder, so to speak, or B, we just get something and we can see a pattern that's just clearly going to be repeating. But a pattern hasn't formed just yet. So 20 minus 16 is 4. 8 won't go into 4 cleanly. So again, we can give ourselves another 0. We can give ourselves zeros till we're blue in the face. We're going to bring that 0 down. And now how many times does 8 go into 40? 5 times. And it does so cleanly. Come on in. It does so cleanly. What I mean by cleanly is now there's no remainder. There's no remainder, and we are done with it. We don't need to keep giving ourselves zeros, nothing like that. Sometimes you might. It just depends on what you have. It just depends on what you have. But here we don't. So what I can say is 5 divided by 8, or 5/8, is equivalent to 0.625 in decimal form. That's exactly how I write it. 0.625, 0.625. If you wanted to round it to 2 decimal places, that would be 0.63, and you can do that, just depending on the situation. And that's all about there is to that one. Now, let's say we wanted to go back. Let's try out the other one, 7 divided by 11. So we're dividing 11 into 7. Let's do that one together, because I think it would be very beneficial. Clear out the previous whiteboard. So we're doing 7 over 11. Maybe we could do one that's a little more interesting. How about 18 over 11? Which you might recognize as an improper fraction. It is improper, technically speaking, just because the top is greater than the bottom, but who cares? Like, that doesn't matter. They like using those mixed numbers so that you know, oh, it's between 3 and 4. But we can figure that out using our decimal division method that we just developed here. We're doing 18 divided by 11, so we're dividing 11 into 18, like so. Now 11 will go cleanly into 18, but we want to kind of figure out how many decimal points out we need to go. So I'm just going to go ahead and give myself a decimal point and a 0, and I know I can give myself as many zeros as I want. And now bada bing, bada boom. How many times does 11 go into 18? It's only going to go in one time. (18 minus 11 is 7. Bring this 0 down. 70. How many times will 11 go into 70? 6 times. And then you can give yourself another 0. What we're going to see is this is going to end up being a non-terminating decimal. It's not going to ever stop. You can bring this 0 down. How many times will 11 go into 40 now? 3 times, exactly. We'll go in 3 times. That's 33. Wait a minute. Wait just a darn New York minute. We get a 7 here. We already know what's going to happen next. We got a 7 here, so we're going to end up saying it goes in 6 times, minus 66. Then we're going to get a 4, say it goes in 3 times, 33. 40 minus 33 is going to be a 7. We're going to keep alternating 7, 4, 7, 4, 7, 4. In other words, we can already see a pattern starting to form, and that's exactly what happens, and it's one that never stops. It's going to keep going and going and going. Blah, 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 dot, dot, dot. That's my lame attempt at a dot, dot, dot. It's going to keep on going and going and going, like the, what is it, the Duracell rabbit, whatever. So 18 divided by 11 is equivalent to, no, don't you do that. Sorry, I tried to drag my screen off. 1.63. Now, the 6.3s keep going forever. They never, ever stop. They go on forever, but they repeat by that pattern. So instead of saying I'm just going to keep writing it over and over and over, I'm going to put a vertical bar above it. So 18 over 11 is equivalent to 1.6363636363, and so on and so forth. And that's my final answer. Now you might need to round it. If you wanted to round to 3 decimal places, then you would have to go 4 decimal places out to figure out the rounding. But we'll actually cover rounding in detail a little bit later on in this semester, very soon, really, if you think about it. Can everyone see everything on the board okay? Is it making sense? In here, you guys good? I just like to stop a little bit, slow things down. Okay, so we did 5/8, but then we did 18/11 because that's a little bit more interesting, at least in my book. See? Now, decimal points. So we know we can convert from fractions into decimals just by using division, just by using the definition of what a fraction is. Well, what if we wanted to go backwards? What if we wanted to go back in time? If we want to do that, we need to pay a bit of close attention to exactly what's going on here. When you're talking about decimal points, you have the decimal point. If you go to the left of the decimal point this way, you're getting larger and larger numbers, and they're whole numbers to the left. If you go from the decimal point and you go to the right, you're getting smaller and smaller. Your first decimal point is the tenths, the hundredths, the thousandths, 10,000ths. Notice the TH at the end. So it's pretty straightforward. You're getting smaller and smaller as you go to the right on decimal points. Well, what that means then is that you can take numbers that start off as decimals and you can turn around and rewrite them as fractions. So we can go from fractions to decimals like we already did, but now we can go from decimal to fractions. So let's look here. Let's see, we've got 0.7. Okay, that's interesting. We only had to go 1 decimal place out. We only had to go out to the tenths place. Thus, we can write it as 7/10, tenths place. This next one, 0.49, well, let's do it together. Let's see, 0.49. How many decimal places did we have to go out here? 2. Yeah, we had to go out 2 decimal places, which is the hundredths. Thus, 0.49 can be written as 49/100. And that's it. Now you would then try to reduce the fraction as much as you can, if you can. But 49/100, I have it on good authority, that's not going to reduce at all. Because 49, its prime factorization is 7 times 7. 100, its prime factorization is 2 times 2 times 5 times 5. Notice the 7's on top, 2's and 5's on bottom, nothing cancels out, nothing crosses out. So 49/100 is what we say, it's in simplest form. But what about this one? 0.036. Well, how many decimal points did we go out to in that case? We went out to 3 decimal points. The 3 decimal points is now the thousandths. It's that many thousands. So you could write that as 0.36/1000. And it is accurate, but remember with whole numbers, zeros in the front don't matter. So you could just say it's 36 alone over 1,000. Now, can that be reduced? Yeah, it looks like it can. Looks like they're both divisible by 2, right? They're both even numbers. So 36, we could divide 2 out of them. What's 36 divided by 2? Let's think. 36 divided by 2, and it'll be 18. Yep. 1, 2 goes into 16 8 times, and it does so cleanly. There's 0 remainder. So we get 18 on top. Some of you may not know this, but I'm actually 18 years old. I'm 18, and I know I don't look it. It's because of some science experiment gone awry. How many of you believe me? Everyone believes me. Thank you for believing me. I know you don't really believe me, but I appreciate the vote of confidence nevertheless. No, I'm not actually 18. Nor am I 36, though. I'm not that old. Not that it's a big deal to be 36 or anything. It's just I am not yet 36. I got some years left before then. So we divided the top by 2. We got 36 down to 18. We have to do it to the bottom. So what's 1,000 divided by 2? Yeah, 500 exactly. You got $1,000 in your bank account. Maybe some of you would rejoice if you had $1,000 in your bank account. You'd be happy about that. And whoop, not 5,000, dung, just 500. Excuse me, got carried away. And if half of your money had to go to rent or child support or something like that, you'd have 500 left over. But wait a minute, is that in simplest form? No, 18 is divisible by 2 nevertheless, or yet again. 500 is also divisible by 2. So what's cool is that means all the way back in the original fraction, these numbers are actually both divisible by 4, because I could divide a 2 out of them cleanly twice. And so 18 divided by 2 is 9. 500 divided by 2, you have $500 in your bank account. Your electric, all your bills come out to $250. That's half. So if half your money had to go to bills, it becomes $250. So we started with 0.036. That's the decimal expression of this number. That one way to write that is 36 over 1,000, and that's a perfectly accurate way to write that. But it can also be written as 18 over 500. It can also be written as 9 over 250, and it turns out 9 over 250 is not going to reduce anymore. 9 can really only be reduced by 3s. 250 is not divisible by 3, so you're done. What's also interesting is notice how I'm using equal signs. That is exactly correct. 9 over 250 is the exact same number as 18 over 500, which is the exact same number as 36 over 1,000, which is the exact same number as 0.036, which is the exact same number we're going to find as 3.6%. They're all the exact same number, just different representations of it. Just a different way of seeing the same thing in each case. So that's cool. Everyone say cool. You guys still use cool? Is cool, or is that dead? Is it a dead Latin word? You say cool? That's cool. All right. We still got cool floating around out there in the stratosphere. That's good to hear. Now, how about a tough one there? A tough one there, Pilgrim. Well, this one's actually going to look, these ones, I kind of wish they would just let those ones go, but they're going to go ahead and do that. What if you started with a repeating decimal number, something that repeated the same pattern over and over and over again, and just never terminated? How do you write that as a fraction? How do you write that as a fraction? Well, they use this cute little formulation here. We'll go through it together. But in my book, you know, it's a bit much. So they use a cute formulation here. So back to the whiteboard with us. Let's clear this off. Okay, the first person who shouts a color, I'll use it for this next point. Blue. Blue it is. Dabba-dee, dabba-da. We use the darker blue because darker blue is easy to see. Okay, so we want to express the number 0.6 where the 6 is repeating. So that's not 0.6 actually. That's really secretly 0.6. 6, 6, 6. I'm going to write one more 6. That's really what that number is. And that's a dot, dot, dot at the end saying it goes on forever and ever, repeats that pattern. This actually creates a really interesting connection. A number is rational if, when you write it as a decimal, it either stops, it terminates, like 0.625 stopped and there's nothing left, or if it goes on forever like this, but it does so via a repeating pattern. It does so via a repeating pattern, which this does here. So 0.66666 all the way to the end of time is indeed a rational number. But what they're going to do is they're going to do some real silly trickery here. They're going to use some math magic here. They're going to say, okay, let's say the number you have, you're trying to write it as a fraction. That's our goal. In fact, I'll write that here. Write as a fraction, ideally in lowest form, in simplest term. Well, we're going to use the variable, lowercase n, to represent the number that we're trying to write as a fraction. Now, for now, we have that as this number. Blah, blah, blah. Here's a silly little trick they're going to do. What they're going to say, and I'm not a big fan of it, but whatever, they're going to say that, let me just move this down. Actually, they're going to say if we took 10 times that number, in other words, if we took 10 times n, we're going to write it on its own line. Now think about it. When you multiply by 10, or really any power of 10, 10, 100, 1,000, 10,000, life becomes awfully easy for you because multiplying by 10 in this case means move the decimal point one place to the right. So that's really useful information. What that means then is 10n is the number 6.6666, blah, 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 blah. Everyone tracking so far? It's a little bit of a weird thing. We're just playing around with numbers a little bit. Why are we doing it this way? Some mathematician figured out it's a neat little trick. Now here's what we're going to do. You may not know this, but in math, you can subtract equations from each other as long as they're all unified by the same variable, which represents the same number, which is the case here. Our variable n is all meant to represent the number 0.666666. So here's what we're going to do. I'm going to subtract that equation from the top one. That means that I do it on both sides of the equation. And I know we haven't quite talked about variable expressions just yet, but if you took 10 of something here on the left side, you took 10 of something, 10 times n, you subtracted 1 of it, how many things of it do you have left? I got 10 apples, I subtract 1 apple, how many apples do I have left? 9. So when that happens, that becomes 9n over here. But the cool thing is on the right-hand side, okay, I do the subtraction, and all that's left is that 6, because it's 6 minus 0, point, but all those 6's after the decimal point took care of themselves. They're all gone, baby, gone. In fact, I don't even have to write them. I'm able to just say, hey, just comes out to 6. Oh, that same number, n, that we're trying to solve for, can be written as 9 times n equals 6. So now to get n by itself, and again, they're kind of previewing a little bit. To get n by itself, we need to divide both sides by that 9. This means that n equals 6 over 9, which reduces to 2 over 3 if you divide a 3 out of the top and bottom. And that's our answer. The number 0.666666666 repeating forever and ever and ever just reduces or just becomes the fraction 2/3. And if you don't believe me, get out of here. Look, 2/3, you can divide 3 into 2 using that little decimal trick that we used earlier, and you'd end up with 0.6666666. you would see the repeating pattern. Ain't that something? Well, I sure think it is. So now we got to talk about, all right, we got rational numbers, we got fractions. We can't let fractions scare us. We got to try and just breathe a little bit, let the fractions kind of flow over us, and we can be happy and we can be successful. Here's what we can do. We're going to end up adding, subtraction, multiplying, and dividing fractions. We're going to learn the exact process behind that. The thing is, adding and subtracting fractions is actually harder than multiplying or dividing by fractions. It's actually the harder process, believe it or not. Or maybe you do believe me because you've seen it before. The reason is that adding and subtracting fractions requires us to have something called a common denominator. Multiplying or dividing fractions does not require that. If I want to multiply two fractions, they can be any two fractions. A over B, we'll call that the first fraction. C over D, we'll call that the second fraction. If I want to multiply them together, I just kind of smoosh them together. I multiply the numerators together. I multiply the denominators together. And bada bing, bada boom, I make that new fraction. I make it. It just kind of works like that. We just smush two things together. Okay, maybe you like that, maybe you don't. Looks like we have someone chatting over. Thank you, Xavier, for saying cool earlier. Very good. That's very apt. I appreciate that. So multiplying two fractions is really straightforward. Let's say we want to multiply. How about, okay, someone else give me a different color. Purple? Purple works. We'll use this one. That might be striking. That's as close to purple. It's a little more pink, but we've got to deal with what we have, right? Can't help it. That's what we say. We want to multiply 2/3 times, and I like to use that little dot for times. I don't like using X for times because X is a variable we're going to use a lot, and I don't want it to get uber confusing. Let's say we're going to multiply 2/3 by, what's an interesting one? How about 9/8? Two-thirds times 9/8. Well, like I said, we're multiplying. All we do is multiply across the top. So on top, we do 2 times 9. On bottom, we do 3 times 8. So all my mathketeers out there, what's 2 times 9? 18. On bottom, what's 3 times 8? 24. Darn Kiefer Sutherland. How is 18/24, is that a reduced fraction in simplest terms? No. How can that reduce? Well, we could divide a 3 out of the top and bottom. Maybe start with that. Turns out we could also divide a 6 out of the top and bottom. Let's try just dividing a 3 out. 18 divided by 3 is 6. 24 divided by 3 is 8. Does 6/8 simplify? Yeah, what does that become? 3/4. Yep. The top and bottom can both have a 2 divided out there. Very good. So 2/3 times 9/8 is equal to 3/4. But let's mess around with that a little bit. How many of you feel like messing with something? Maybe you want to screw with it. Maybe just a little bit. Have some fun with it. We know the answer is 3/4. That is the true, blue, golden, correct answer here. Whoops. Need the eraser for that. Yoink. Looks like a game or something. So we have it down to 2 times 9 over 3 times 8. Let's play around with it. Before we actually multiply the 2/9 and the 3/8, Let's actually write them in their simplest forms. 2 is a prime number, so I'll just rewrite it. 9, though, can be written as 3 times 3, can't it? Absolutely. Yeah, I could write it like that. 2 times 9 is the same as doing 2 times 3 times 3, because the 3 times 3 would have been 9 anyways. On bottom, 3 is already in simplest form. How could 8 be rewritten? Exactly. You can write it as 2 times 4, but then the 4 would expand some more. So you can write 8 as 2 times 2 times 2. And that's all multiplication there. And now the bottom's not written in order. That's okay for this moment. So now we shall slash through our enemies. This 2 and this 2 can cancel out completely because everything's being multiplied on top. You throw a plus sign somewhere in there, get out of here. It doesn't work anymore like that. You gotta mess with it a little different. And then this 3 can cross out with this 3. And what we're left with is just 3 on top. On bottom, we're left with 2 2s, or 2 times 2, which is 4. So that's another way we can simplify fractions. We can write them, we can find their prime factorizations on top and on bottom, and any common numbers we can cross out, we can slash them out like that. And all we have is what's left there. There is even yet another way to do it. There's even yet one more way to do it. So we got 3/4, we did it one way, but we kind of got some large numbers at the end and then had to decide how to simplify. What we're doing by using this prime factorization method is we're simplifying before we get to the final answer. So that by the time we get to the final answer, it's already done. It's already in the books. We can go even one more way, and this last one here is going to be the preferred way. There we go. So all the way back to the basics, 2/3 times 9/8. The first thing we do is we check that each individual fraction is in simplest form. We can see that 2/3 is already in simplest form. We see that 9/8 is already in simplest form. If they weren't in simplest form, go ahead and put them into simplest form as individual fractions. But now we can do something magical. We can do something wonderful. Something called cross-multiplying. Cross-multiplying. It's a useful trick. Once you know your two fractions are already simplified as much as they can get, now we're gonna look at things across the way from each other. So we have 2 and we have 8 looking across the way from each other. Do you know the way? Let's show you. The 2/8, you can think of it as almost like 2/8, like the fraction 2/8. And how would you simplify the fraction 2/8? If you had 2/8, you'd simplify it to 1/4. 1/4. So guess what? We can do that right now. The 2 and the 8, we can simplify them to 1 and 4. So again, we're pre-simplifying before we even multiply so that it makes our lives easier. Cross-multiplying is gonna be a vital skill we're gonna want to develop. Now, we look at the other way, which is 9 and 3. If you had 9/3, 9 divided by 3, how would you simplify that? Exactly, perfect. 3/1. Oh, that's not so bad. Just check this. Now I do the multiplying, but now that I've crossed the numbers out on top, along the top there, why does it keep doing that? Along the top there, I'm just doing 1 times 3. 1 times 3 on top. On bottom, I'm just doing 1 times 4. Get out of here. That's just 3/4. And we already know 3/4 is the correct answer, and it's in simplest form. We can't make it any simpler than that. So let me take a quick swig of water. I will turn my face so so that I do not expose any of you to my water droplets. 1 second. Ta-da! No water droplets got out. Well, now my hand's wet, so I can't use it on the whiteboard. That's okay. So get out of here. Multiplying fractions, the process is straightforward, but usually you want to simplify before you really go into it, before you jump in. So here you go, blah, blah, blah. The only thing to note, so this is very close to what we ended up using. The only thing to note here is that if you have negative numbers, just remember the rules don't change. Fractions are just like any other number. They're not special, they're not anointed and put above the rest of the matting crowd. Fractions are just like any other number. So if I had a negative number times a negative number, you know the answer has to come out positive. So once you know that the answer is going to be positive, then just multiply the fractions like they were both positive. Or if that was negative 2/3 times positive 9/4 to start with, you know your answer has to come out negative. So just slap a negative sign wherever you plan to put your answer, and then you can ignore signs and do the actual multiplication. Dividing rational numbers. So you can add, subtract, multiply, divide. What we're going to do is we're going to do multiplying first, then we're going to do dividing. Well, ladies and germs, here's the cool thing about dividing. You might remember last week I said that addition and subtraction at the end of the day are the exact same process in a way, in a special way. It's the same thing is true for multiplying and dividing. It turns out if you wanted to divide one fraction, a over b, by another fraction, c over d, you use a little process called multiplying by the reciprocal. You flip the second fraction, the one you're dividing by. You literally flip the top and bottom upside their head and turn it into multiplication. And that's it. You're done. That's how you divide it. So then you just got to go and do the multiplication as proper. So let's try this out. Don't look at the answer. Negative 3/5 divided by 7/11. Negative 3/5 divided by 7/11. Well, I've got a negative number dividing by a positive number. But before we even deal with that, oh, there's purple. Let's turn it into multiplying by the reciprocal. The 7/11 is what we're dividing by, so we're going to turn this into negative 3/5. The first number does not change, times flippity flop. Negative 3/5 times 11/7. Now I notice my first number is negative, my second number is positive. When I multiply a negative and a positive number, what kind of number do I get out of that? Negative, exactly. So the overall answer is going to be negative when I'm done. And then once you know what the final answer is going to be, you know that it's going to be negative. You can kind of play pretend and act like you didn't have a negative to start. It's still there, but it's kind of pesky. We're going to ignore it because we already dealt with it. And now we just basically now have 3/5 times 11/7. Now 3/5 is in simplest terms. 11/7 is in simplest terms. Now, when I try cross multiplying, I look at the 3 across to the 7. Is there any simplifying that can be done there? No. If we had 3/7 as a fraction, it would be in simplest form. So no cross multiplying we can use there. What about 11 and 5? Do those help each other out at all? No. If I had the fraction 11/5, then, wouldn't help me. So there's no cross multiplying trick we can do here. So if there's no cross multiplying, and I know each fraction started off in simplest form, my final answer is also going to be in simplest form. There's nothing to simplify along the way. So now we know it'll be negative. Across the top, what's 3 times 11? 33. On bottom, what's 5 times 7? 35. So the answer is negative 33 over 35, excuse me. And that negative number is loud and proud. We can kind of mute it a little bit, negative 33 over 35. So that's the cool thing about division. It's really just multiplication, just flip a number. That's it. That's it, Chip. That's it. Do what? Yeah, there's all kinds of cool little like mnemonic devices and things you can use to remember. So if you have a system in mind, you know, and you're comfortable with it, you know, we don't have to fix what ain't broke. That's how I see it. So yeah, if you've got a fancy system, by all means, use it, keep it in your mind, and use it. That's not where I want to go. So now let's talk about adding and subtracting fractions. That's where it gets a little bit harder, a little bit more difficult. Now here's what I can say. If I need to add, let's use gold. We're going to say gold and not yellow because gold sounds cooler than yellow. How many of you would agree with me on that? You'd say, yes, that is wisdom. Yes, you're absolutely right. It is. Gold is cooler than yellow. If you were to add two numbers that had the same denominator, A over B, that's not easy to see. So, sorry, gold. You're still cool sounding. Let's try orange. There we go. Orange is a little better. If you had two numbers that had the exact same denominator at the get-go, so A over B, that's not a 9, that's an A, plus some other fraction C, but with the same denominator as previous, B. Or if you did subtraction instead of addition, A over B minus C over D. Not D, I'm sorry. B, they got to have the same denominator. Well, it's tricky. You want to add the denominators. When we multiplied, we would multiply denominators. But here, we don't actually add the denominators together. We don't get 2b or not 2b. We just keep that same denominator. So when you add two fractions with the same denominator, the answer is just going to have that same denominator at the beginning. And then we just add the numerators together. And that's it. Then you might have to simplify the fraction a little bit using our other tricks, techniques, whatever. Subtraction, same thing. Keep that same denominator, don't change it, and just do the first numerator minus the second numerator, A minus C. That is cool and the game. So in the case that you have the same denominator, it's peachy keen. It's pretty straightforward to add or subtract fractions from each other. We can do an example. So let's say you had 5 over 15. And notice that 5 over 15 is not in simplest form. That's okay, because we're going to add it to, how about 7 over 15. Now you're tempted to say, well, Josh, we should put 5 over 15 in simplest form first. Not that any of you would have a nerdy voice if you're asking me about that. You're nerds. I'm the biggest nerd in the room. How many times have I watched Battlestar Galactica? I won't say. I'm not exposing myself like that as a nerd, no. But we wouldn't want to reduce 5 over 15 to 1/3 to start with, because then we wouldn't have the same denominator anymore. And we'd have to go back to get a common denominator. So it's usually only in the last stage, or maybe if you're trying to simplify along the way, do you actually want to simplify your fraction. But here, it actually helps us that it's written like this. Because the answer, we don't add the denominators, we don't try to say it's 30. On top, we do 5 plus 7. What's 5 plus 7? 12. And now that we've done the addition, does 12 over 15 simplify? Are you sure? Methinks it do. 12 over 15. Can we divide a 3 out of the top? Yeah. We can divide a 3 out of the top. 12 divided by 3 is 4. Can we divide a 3 out of the bottom? Well, we better be, because we can't proceed unless we already knew that. Yeah, we can. So 12 over 15 reduces to 4 over 5. If you wanted to figure out what 4 over 5 was as a decimal, divide the 5 into the 4. It'll come out nice and clean, just so fresh, so clean. Oops. 5 goes into 40 8 times. There'd be a 0 remainder. So if you wanted to know, 4 over 5 is equal to 0.8 if you express it as a decimal. Subtraction, same idea. Subtraction, let's say you wanted to use, I don't know, 13 over 17, and you're subtracting the number 21 over 17. Well, we know that the fraction is going to keep that same denominator. It's certainly better, because now we don't do 17 minus 17 on bottom, because that would give us a 0 on bottom, which creates a problem. So adding and subtracting fractions just doesn't work like that. We just keep that same denominator. And on top, 13 minus 21, and so we're taking a larger number away from a smaller number, so we know that's going to end up being negative. Now, however you do it, you could say that's negative, it'll be 17 on bottom. So now that you know it's negative, now you actually do the 21 minus the 13, and it becomes negative 8 over 7. You could draw a number line to rehash from last time. You start with 13, you subtract 21 from it, you're gonna go blah, 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 blah. You're gonna go 13 units, it's gonna get you to 0, but you're not done. You gotta keep going into the negative realm. You got 8 units left over, blah, blah, blah. So it's going to be negative 8. So if I do 13 minus 21, I get negative 8 over 17. Is negative 8 over 17 simplified? Oh, I don't know. Yeah, it won't. 17 is a prime number, so it probably won't simplify unless the top number is a multiple of it, which it's not. So yeah, now if it was 8 over 16, then you could talk. But 8 over 17 doesn't simplify at all. So let's take a quick breath. Do you guys have any questions on this so far? Is it pretty straightforward? We've seen this kind of material before. Maybe this is a refresher for you, just depending on what you're doing. And now, that was pretty straightforward. If you have the same denominator, then adding and subtracting fractions is not so bad. It's not so bad. But it's time to take away your joy, take away your happiness. We can add any two fractions we want at the end of the day, or at least we should be able to. Well, unfortunately, what we might have to do is get a common denominator if they're not the same denominator, if each fraction doesn't have the same denominator. That's going to make things confusing. Now, what they're prescribing here is that you multiply the top and bottom by the same number in order to get common denominators. And that is essentially what we're going to do. But let's try explaining it in a slightly different manner. Let's say you have 5 over 8, and you're adding to it, how about 11 over 12? 5/8 plus 11 over 12. Do those have the same denominator? No, they do not. So can I just do this? Oh, just add the denominators, and I'll add the numerators. Does that work? No, it doesn't work. Remember, no, that's not how it works. You can only add or subtract two fractions if they have the same denominator. If you're multiplying, we wouldn't worry about it. But here we have to worry about it. All right, so back to the drawing board. Here's what we're going to do. We're going to look at the denominators we do have. We've got 8 and we've got 12. And now what you're going to want to do is you're going to want to find the least common denominator. But what that really is, what that really truly is it's just the least common multiple of all the denominators. So it's a little bit confusing because you're saying least common, but your denominator is actually going to get larger here in a second. So it's the least among the larger numbers that you could get. Okay, so our denominators are 8 and 12. So let's come over here. We want the least common multiple then of 8 and 12. Well, remember, we can do this by listing out the multiples of 8. So it's going to be 8 times 1 is 8, 8 times 2 is 16, times 3 is 24, times 4 is 32, times 5 is 40, times 6 is 48. And it keeps going and going and going and going. As Fred Durst said, it keeps rolling. So we can keep going after that. It's going to have an infinite number of multiples, but maybe we don't need to go out that high. Let's look at 12. 12 times 1 is 12, times 2 is 24, then 36, then 48. Ooh, I see something there. You keep going, you get 60, you get 72, blah, blah, blah. We want the least common multiple. Here's all the multiples. Now, 48, 48 is a common multiple, isn't it? It's both a multiple of 8 and 12. But is it the smallest one? No, it is not the least common multiple, because you see they also share a 24. And that's going to be my least common multiple is 24. So we'll call it the LCD, which is just the least common multiple of the denominators. The LCD is 24. Now here's what we're going to do. We all know that there are athletes out there who use human growth hormone, which is a fancy way of saying steroids. It's been a huge problem in all the major football, baseball especially. Let me say that again. Baseball especially has deals with it, problems with it. We're going to use some steroids here. How many of you are ready to use some steroids? Not literal physical steroids, because I'd probably be arrested if I supplied you with steroids. Also, they're very expensive. You know, they're very expensive. How do I know? Well, I took steroids for a period. No, I'm just kidding. I've never taken steroids in my life. We're just playing around. We're just having a little fun here. I'm gonna give myself a little space. Here's what we're gonna do. We found the least common denominator to be 24. Here's what we want then. We want this guy to be a 24. We want this guy to also be a 24, or girl. We want them to have the same denominator. Well, here's the thing. I can multiply a fraction by anything I want as long as I do it to the top and bottom. So what would the 8 need to be multiplied by to get it up to 24? 3, exactly. If I were to multiply the bottom by 3, real quick, but am I allowed to just do it to the bottom? No, I have to be fair. If I do it to the top and bottom, what it's going to do is it's going to change the way the fraction looks, but it's not going to change the true value of the fraction. 5/8 will become a different fraction that's over 24, but no matter what, the decimal is 0.625. Now to this other fraction, what does the 12 need to become a 24? 2, it needs to be multiplied by 2. But I got to do it to the bottom, or to the top as well. And so now my first fraction, 15 times 3 on top, or excuse me, 5 times 3 on top becomes 15. The bottom is the 24 that my heart desires. The second fraction, on top I get 22. On bottom I also get 24 as I wanted. If I didn't have the same denominator now, I've made a mistake somewhere, I've used the wrong number. But since they have the same denominator, oh happy day, the answer is going to have that denominator. And then on top you got to do 15 plus 22. You can do it, but you should see that it comes out to 37. Hey, bada bing, bada boom. Right? You got 37 over 24. Does that simplify it all? And it looks like it won't. 37 is actually a prime number. So the bottom is not prime. It's not a multiple of 37. So we're done. So we go all the way back to the beginning. And we just look at 5/8 plus 11 over 12. The answer to that is 37 over 24, and that doesn't simplify. Okay, let me take attendance real quick, and then we'll take our little 10-15 minute break. Oops. Okay, so if you're in Zoom, hang with me real quick. I'm going to pause the recording of this. Alrighty there, Pilgrims. Let's get back to it. Okay, so we're going to look at a quick example of where we might use fractional multiplication in real life. I know that's a popular phrase that goes around. A cookie recipe calls for 5 dozen cookies and requires 3/4 of a cup of sugar. Now that doesn't sound right at all because 3/4 of a cup of sugar is not a lot of sugar at all. I want a lot of sugar in my cookies. Do I look like a man who's going to eat cookies that are like nasty diet cookies? No, that's firewood. All right, that's another word for firewood. If you go to foreign countries and it's really cold and you need firewood, sometimes the word for it is, could I get sugar-free cookies? And they'll hand you a bunch of nasty firewood. So if 5 dozen cookies calls for 3/4 of a cup of sugar. So 5 dozen cookies, you want 3/4 cup of sugar. Well, the question becomes, how much sugar do you need for 8 dozen cookies? Okay, so there's a number of ways that we can set this one up. The first thing you could do is you could take 3/4 and you could divide by 5, and that's how much you need for 1 dozen cookies. In fact, that's the way I'm going to feel like doing it. So if I take 3/4 a cup of sugar, and divide by 5, I'll have how much sugar I need for 1 dozen cookies. All right, so I'm going to take 3/4, I'm going to divide by 5. This is kind of like finding a rate. Now the slick way is to just use a proportion, but we haven't covered those yet. Let's not get too wild with it. So I'm going to divide by 5. Well, wait a minute, Josh, says you. How do I divide by 5? Exactly, you need to re-express 5 as the fraction 5/1. Very good. That's how we get a starting point. So any whole number, you can automatically rewrite it as a fraction and just put that number over 1, and you're done. And now that I'm dividing by 5/1, how do I turn that, or how do I actually deal with that? Yeah, exactly. Use the reciprocal. Switch the 5/1 to 1/5 and turn it into multiplication. And now we're going to multiply two fractions. The first fraction is in simplest form, 3/4. The second fraction is in simplest form, 1/5. There's no cross multiplying that can happen. Nothing unique or interesting is going to happen there. So I'm ready to just do it. I'm ready to just multiply. Multiply across the top. 3 times 1 is 3. On bottom, 4 times 5 is 20. So while we don't have a little cup measures that are 20ths, it's still technically how much sugar we'd use for one cut, or for one batch or 1 dozen cookies. So we use 3/20ths of a cup of sugar for 1 dozen cookies. How can we now utilize that information to figure out how much we'd use for 8 dozen cookies? Multiply by 8, that's exactly right. That hopefully your intuition tells you that. Just because you're dealing with fractions doesn't mean that everything you know about math goes out the wall, goes out the door. If we use 3/20 of a cup of sugar per 1 dozen cookies, then if we just multiply by 8, we can figure out how much we'd use in 8 dozen cookies. And then 8, just to make everything smooth, I'm going to write 8 as 8/1, although you technically don't even need to do that if you understand how it's going. You're multiplying that 8 to the numerator. Now let's pre-simplify before you multiply. 3/20 is in simplest form. 8/1 is also in simplest form. But now let's cross multiply. The 3 and the 1, those don't simplify anymore. But 8 and the 20, can that simplify? Yeah. Imagine you had the fraction 8/20. What would you reduce that to? What's that? Close. You're very close. We could divide a 4 out of the top and bottom. So 8/20, if we divide a 4 out of the 8, we'd have 2, exactly. And then 20, we could divide by 5 and get, excuse me, we take 20 and divide it by 4 to get 5. And now I do the multiplication. I do 3 times 2 on top, 6. 5 times 1 on bottom, 5. So 8 dozen cookies requires 6/5 of a cup. So that's 1 1/5 cups. That's a little bit more than 1 cup. You need a little over a cup of sugar. Well, what's interesting is, maybe you know this, maybe you don't, you can't divide. There's no 1/5 of a cup measurements, so you might have to eyeball it and it won't be exact, perfect. But you can get close to it and get closer to fine. Okay, so that does it over rational numbers, which is a fancy way of saying fractions. Let me pull up our next set of notes. Okay, here we go. Bada bing, bada boom. We're going to call them irrational numbers. Irrational numbers, these are numbers that are not rational. Now, you remember last time we broke down the number system. We said, boom, you got natural numbers. Those are positive whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7. You have the integers, which includes the natural numbers, includes 0, and it also includes the negative forms of all the natural numbers. So -1, -2, -3, -4, -5, etc. 0, and all the positive numbers. Then we have the rational numbers, which are all the possible fractions that can be formed as a ratio of two integers. Now we can deal with numbers that are not rational. Numbers that are not rational. Irrational, you put that IR in front, it's like taking the opposite of it. The set of irrational numbers is the set of numbers whose decimal representations are neither terminating nor repeating. What is it? Let's repeat that. Let's repeat that. Remember, when we did 5 over 8, we wrote 5 over 8, and we found out that as a decimal, 5 over 8 was 0.625. And then we were done. It didn't go on forever and ever after that. That's called terminating, because at some point it just stops and you don't need to keep going with it. That is an example of a rational number. Any number that terminates is rational. That includes whole numbers. 6 is just the number 6. It's not 6.03842, blah, 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 blah. It just is 6 and it's done. So all our whole numbers, negative whole numbers too, 0, those all terminate. They stop. They don't have to keep going on forever and ever. So those are also rational. So a rational number is one that terminates, or if it does go on forever and ever, it does so via a repeating pattern. You recall that we did this earlier. We found 2/3. We actually started with the decimal. We found out 2/3 is equal to this. And the sixes keep going and going and going. Well, it's okay for a number to go on forever as long as it does so via a repeating pattern. Here the 6s are repeating. But even like the number 1 over 7 is a repeating pattern. It takes 7 digits before it goes, but it will eventually repeat itself. So a rational number is one that either terminates or it repeats going forever and ever. An irrational number then, it can't terminate. If it's the opposite of rational, it can't terminate. Also, so not only does it not terminate, it keeps going forever and ever, it has to keep going on forever and ever without repeating the same pattern ever. It never repeats itself exactly the same way twice. So that's what an irrational number is. So automatically an irrational number is something that has to be expressed as a decimal, and it's going to keep going forever and ever with no definitive pattern. The classic example is written here, pi. Pi is 3.14159265358979322 blah, blah, blah. It's just what you see there. Do you see any patterns forming? No, there's not a pattern forming. And there's just truly, honest to goodness, no repeating pattern. So pi is actually a classic example of an irrational number. You remember pi from circles is the ratio of what? A circle's circumference to its diameter. If you take a circumference divided by a diameter, you get pi. Let's see if should. No. Let me kill this annotating thing. Come on. Oh, there it is. So we know that pi is the classic example of a repeating number, or of a number that goes on forever without repeating. But a square root also has a possibility to give us an irrational number. Now remember what a square root is. So when you take the square root of a number, especially the principal square root, you're asking, okay, the square root of 36, what is a number that when multiplied to itself gives me 36? So what's the answer there? 6, exactly. The square root of 81 then, you say, what's a number times itself that produces 81? And it would be 9, exactly. So there's some clean square roots. The square root of 81 is 9. And when we use this symbol, this house symbol, we're taking what's called the principal square root, and we only want to deal with the positive square root. So the square root of 81 is 9. But what's the square root of 80? Everyone go, ooh. Everyone go, ooh. Everyone go, ooh, with enthusiasm. Even out there in the Zoomosphere, is the right answer. It's not going to be pretty. It's not going to be pretty. We got some people going, out there. Let's see. I wonder how they would type out, only at Mattress Giant. Very good. So yeah, the square root of 80 is, it's not going to be pretty. The reason for that is that 80 does not have a number that multiplies to itself and creates 80 cleanly. There is a number that does it, but it's ugly. It's a very ugly number. So the square root of 80, there is something. There is a number that does it, but it's not pretty like 9 was. So here's the deal. When you take the square root of a number that doesn't have a clean square root, you're almost always going to get an irrational number if you know what you're doing. So the square root of 4 is 2. So square root of 4 is not irrational, it is rational, because it comes out to the number 2. But if you took the square root of 5, suddenly there's no two numbers that no number that multiplies to itself and gives you 5, and that number is nice and clean. And so that's kind of the warning that they share down there. So for us to really understand these, we need to know some of the first amount of perfect squares, we call them. Perfect squares, and I'm going to create my own because I am a true learned man of science. So let's look at some perfect squares. Yeah, they did 0 squared first. So when you square a number, you're multiplying it to itself. 0 squared is 0. When you take the square root of a number, you're going the other way. When you do 0 squared, you're saying 0 times 0, which of course is 0. You take 1 squared, you're doing 1 times 1, which is of course 1. 2 squared, 2 times 2 is 2 is 4. 3 squared is going to be 9. Oh my gosh, getting ahead of myself there. 4 square is going to be 16. So on. 5 squared is 25, 6 squared is 36, 7 squared is 49. It would be beneficial if you memorize the first 15 to 20 squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So when you square a number, you're multiplying it to itself. So this is camp A. Camp B, when you take the square root of a number, you're going backwards. Instead of multiplying it to itself, you're asking, hey, what is a number that when multiplied to itself produces the thing I'm taking the square root of? So the square root of 4 is 2 because look, because 2 squared is 4, the square root of 4 is 2. So we're just kind of reversing the process of squaring something and multiplying it to itself. But what that makes is something interesting. That means the numbers that are nice squares, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 39, 8 squared is Nintendo 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, etc. If you were to keep going and going and going, these are what are called the perfect squares because they are the square of a nice whole number that's easy. Thus, all of these numbers can have their square roots taken, and it's nice, straight up, and easy. But if you go anywhere in between, hey, look, here's 7. 7 is between 4 and 9. The square root of 7, and let me write that a little better. The square root of 7, and this is an old joke, is going to be ugly. You know what, I won't make the joke. I had a joke lined up, but I won't do it. I'm going to be nice today. How many of you like it when I'm being nice? You say I'm going to be nice. Okay. I don't know if that's a fair poll or not, but the square root of 7 is going to be ugly. Now, we can bust out our little phone calculator. I know it's going to be between 2 and 3. But let's see, Mr. Phone or, 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 the square root of 7, if you write it out, In decimal form, it's going to be 2.645751311064591. Now your phone calculator stops. That's as far out as my phone calculator goes. You turn it on its side. It actually doesn't stop, but it doesn't really stop. It goes forever and ever with no repeating pattern. It doesn't stop. Your phone has to stop at some point. You can't spit out an infinite number of digits. It's impossible. So it does have an infinite number of digits. So really, it should say dot, 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 dot. It keeps going, and there's no pattern. There's no repeating pattern. I don't see a pattern starting to form here. Anyone else? Do you guys see a pattern starting to form here? No. So that's what it means to be irrational. So most of the time when you take a square root, if you don't take the square root of one of these clean, nice, even squares, you're going to get an irrational number. If you tried something between 49 and 64, I don't know, how about 57? Well, the square root of 57, you can go check it out in your calculator. It's going to be some nasty nast. It's not going to work out. It's not going to be easy. It's going to be a number that's ugly. So all kinds of ways we can generate irrational numbers. Back to the PowerPoint. There's one other type of irrational number, a popular one. We'll probably deal with it later on. We'll definitely deal with it when we get into the Math 1332 portion. But now we really got to delve into square roots, because square roots are going to pop up plenty of times throughout this course. They have to. So if I take the square root of something, A and B, let's say both A and B are non-negative numbers. If I were multiplying on the inside there, A times B, I could split them up into two separate square roots. Why would I want to do that? There's all kinds of cutesy little mathematical simplifications that can be done using this magical product rule for square roots. And vice versa. If I started off by I was taking the square root of one number times the square root of another number, bada bing, bada boom, you're going to end up, you can put them into the same square root house. So let's see an example of this. Let's go right down the line. This first one, if I had the square root of, I don't know, how about 14? If I was so motivated, I could rewrite 14 inside the square root as 2 times 7, couldn't I? I could do that. And if I so wanted to, I could rewrite that as the square root of 2 times the square root of 7 and split them into two separate square roots and then I'm multiplying. Now someone out there say, but Josh, why would you want to do that? Thank you. Thank you very much. You're exactly right. In this case, in this particular example, you might not want to do that. Let's see an example where you would. So square root of 14 maybe it does, maybe it doesn't make sense to split up according to this rule, but let's look at one that might. How about the square root of, I don't know, how about 18? Square root of 18. There's a couple different ways you could write the square root of 18. For our case, let's rewrite it as the square root of inside 9 times 2. Then, according to this rule, I can split that into two separate square roots. The square root of 9 times, separately, the square root of 2. And now, do y'all see any mathemagic that can happen with that? Is the square root of 2, is that going to be a clean square root? No. Square root of 1 will be clean. Square root of 4 will be clean. But the square root of 2 is not going to be clean. It's going to be something ugly. So that can't happen. But will the square root of 9 simplify? Yes, into what? 3. Very good. So this can be rewritten 3 times the square root of 2. Or sometimes we just write that as 3 square roots of 2, we call it. 3 times the square root of 2. Bless my heart. So we've got that one. We can go that way. We can start off by splitting up a square root into two separate square roots. You can do that. You can do that with three numbers. If you had square root of, and then on the inside of the square root, if you had 3 times 7 times 2 times 4, you could do square root of 3 times square root of 2 times square root of 7 times square root of 4. If you wanted to, you could do that. So it's not limited to just two numbers at a time. Let's go the other way. Let's say in this second case, we were starting off with the square root of 2 times the square root of 8. Yes? Exactly, exactly right. So we're done with that one. Square root of 18 over here on the left, agree, can be rewritten as 3 times the square root of 2. You don't believe me? Have I not earned your faith? But that's okay if you don't believe me. Go into a calculator, find the square root of 18. I'm not picking on you individually. You're the royal you know. You take the square root of 18. I don't know exactly what it is off the top of my head, but it'll be ugly. Then you can also separately find the square root of 2 and multiply it by 3 in the same calculator, and you'll get the exact same thing as when you took the square root of 18. So that's a common thing to do in math, is to rewrite things, square root of 18, rewrite them in a different way that's simpler to look at, but they're the same number. 3 square roots of 2 is the same exact number as the square root of 18. They just look different. They're two different representations. Good question. So now back over here on the right-hand side, we got square root of 2, we got square root of 8. There's two separate square roots that we're multiplying together. Now, is the square root of 2 going to come out pretty? No, it won't. It's between 1 and 4, which are perfect squares, so it won't come out pretty. The square root of 8 going to come out pretty? Not quite. There's a way to simplify it, but square root of 8, remember 8 is between 4 and 9. 4 and 9 would come out pretty if we took their square roots, but 8's stuck between them. So individually, square root of 2 is ugly. Square root of 8 is ugly. But if we put them into the same house, into the same square root house, that's the first thing we do. We'd put them into one house and we'd multiply on the inside. And then what's 2 times 8? 16, so it's become square root of 16. Is square root of 16 going to be pretty? Yeah, what is the square root of 16? 4. So wait a minute, Josh, you say in your best Don Knotts voice. If you don't know who Don Knotts is, he was on the Andy Griffith Show. If you don't know what the Andy Griffith Show is, that makes me very sad. That's okay if you don't know what the Andy Griffith Show is. It's from another time. The square root of 2 times the square root of 8, well, both of those individually are ugly. They come together like Voltron, and they actually are the square root of 4, equal to the square root, or excuse me, just 4. They're equal to just 4. So what looks ugly at the get-go is actually not so ugly. This is a common element you see in Disney Channel movies. So this is that product rule for square roots. It pops up. There's some reasons to use it. There's some simplification that can be done thanks to it. So we can see that there's some simplification that can come out of it. What if the numbers are ugly? Well, that's okay. Square root of 75, you can rewrite 75 as 25 times 3, all inside a square root. Split those off into two separate square roots because 25 is a perfect square. And so then that 25 becomes just 5. The square root of 3 is not a perfect square, so it just stays that way. So while square root of 75 will produce an ugly number, we can at least re-express it as a slightly less ugly looking number, 5 square roots of 3. And same thing for 500. The idea is you have a number that's not itself a perfect square, but if you can divide a number out of it that is a perfect square, you can simplify. So since 500, you could divide 100 out of it. 100 is a perfect square, it's 10 squared. You're able to make a little bit of simplification. Square root of 17, that's not going to work. 17 is a prime number. It's not going to factor any other way. So square root of 17 is just done. It's just, it is what it is. Square root of 6. Square root of 6 won't do anything fancy. 6 is 2 times 3, but neither the 2 nor the 3 are perfect squares themselves. There's no point in branching them off like that. So square root of 6 is, as Jack Nicholson would say, as good as it gets. So we can use that property, which really this is just the same thing we just studied up here, this multiplication property. It's just this. We can use that property a lot. That's going to help us simplify things. The important thing to remember, though, is that the numbers at the beginning, the a and b, shouldn't be negative. If you have a negative inside your square root, funky stuff happens. Funky things come out of it. So we're just going to say, well, you can't take the square root of a negative number for now. Let's think about it. The square root of 9 is 3, because 3 times 3 is 9. But what's the square root of negative 9? Can you think of the same number multiplied to itself that produces negative 9? You're going to be racking your brain all day because it's not going to work. 3 doesn't work. 3 times itself is positive 9. Negative 3 doesn't work because negative 3 times itself, negative 3 times negative 3, the negatives cancel and become positive. So you actually can't take the square root of a negative number. But I need to share with you the idea that we might revisit that later. So at this moment, you can't take the square root of a negative number. It's just not going to be valid. It just doesn't make sense when you look at the raw definition of taking a square root. So we can see a few examples of that. If you're multiplying two numbers that were being square rooted individually, square root of 2 times the square root of 5, they're separate square roots. You can bring them into the same house and just multiply their insides like that. So the square root of 2 times the square root of 5 is equal to the square root of 10. That also creates a few other interesting things. If you take a square rooted number and multiply it to itself, the square roots basically just cancel out. So square root of 7 times square root of 7 becomes the square root of 49, which is just 7. That creates a pretty interesting idea in that if you have the square root of any number you want, let's call it x, and you multiply it to itself, square root of x times the square root of x, where as it is written, x is going to give it to you. Well, you're multiplying something to itself, which is another way of saying you're squaring the number. So square root of x times square root of x can be rewritten as, well, square root of x then being squared. The two undo each other. The square root and the squaring are opposite operations of each other. And we just end up with the x we started with at the get-go. We're going to use that property a lot, that the square root and the squaring operations undo each other. They undo each other's effects with a little bit of detail that we have to add to it later. And then the last thing here, there's this cute little thing here. Square root of 6 times square root of 12. Well, individually, square root of 6 is an ugly number. Square root of 12 is also an ugly number. But we have allowed them to branch together. We've brought them together. And now this 12 can be written as 6 times 2. So basically, you're helping to unite two 6s that were in separate square root houses to begin with. And then it still ends up being an ugly number, but it's a little bit less of an ugly number. It's not quite as ugly as it was just a second ago. Boy, you guys at home, I envy you because wearing the mask and then talking for several hours is not fun. It's not a whole lot of fun because the hot air that I'm exhaling is blowing up into my face, and so I feel like I'm sweaty. But I do believe fully in the mask. Don't get me wrong. I'm not saying the mask is bad. Jim Carrey's The Mask is a classic. It's a wonderful film. So now we have multiplying square roots. Hey, we can bring them into the same square root house, or we can split them off. Well, it turns out the same rule applies for division. Because remember, division and multiplication, they're the same thing at the end of the day. They're the exact same process, just they look different, but they're not different. So you can do the same things. We're going to require that the numbers inside the square roots are all positive to start with. or 0, except this denominator can't be 0. So remember, dividing by 0 is never, never, never a good thing. It's always bad to divide by 0, especially at this level in this course. So what can you do with this? What magic fanciness can you bring out? If you have the square root of one number divided by the square root of perhaps a different number, you can bring them all into one house, all into one square root, and then just take the top number divided by the bottom. It sounds obvious. It's actually not. It's actually not as obvious as you think. I'm giving you these rules, telling you that they work. And vice versa. If you're taking the square root of one number divided by another, a square root of a fraction, you can split that into a fraction of two separate square roots if you wanted to. It depends on what the situation calls for. So I'll give you a second to write that down. To me already. And yes, feel free always to ask me clarifying questions on things of the like. I'll try to I have the chat box going on my iPad over here so I can watch myself, make sure you're seeing what I'm seeing. Grab a sip of water real quick. I will never allow any of you to see my full face because that's how I lose my power. I don't know. It's like a Samson thing, I don't know. Okay, so let's look at an example here. Let's say you started with the square root of 75 divided by the square root of 3. Well, guess what? By itself, the square root of 75 is ugly. Square root of 75 is going to be an ugly number. It's between 64 and 81. 64 is a perfect square, 81 is a perfect square. But if you're between two perfect squares, you're not going to be a perfect square. So square root of 75 on top is ugly. Square root of 3 on bottom, ugly. But with a little bit of magic, we can bring them into the same square root house. We're doing the order of operations, we're switching the order. Then we can call that the square root of 75 divided by 3. And that's beautiful because then we can get the 75 and the 3 working together. 75 divided by 3 is 25. And then we're just taking the square root of 25, bada bing, bada boom, it's 5. So this nasty number that we started with, square root of 75 divided by square root of 3, we took a nasty number, divided by a nasty number, and we actually got a clean number out. We got a nice, clean, brand spanking new 5. Everyone say, ooh, very pretty indeed. Same thing down here, it's just a little bit less interesting. We got an ooh down there. Thank you, Nicole. Same thing over here. You got square root of 90 on top, square root of 2 on bottom. Bring them into the same house. Then 90 divided by 2 is 45. So then square root of 90 over 2 just becomes square root of 45. And then you could make the recognition that 45 is 9 times 5. Why would you bother? Because 9 is a perfect square. You can branch it off, and it becomes that. Square root of 5 is not anything special, not anything pretty. So this is our final answer, 3 square roots of 5. So we've got some multiplication of square roots. We've got some division of square roots. There's some simplification we can do. Now, what if we wanted to add and subtract square roots that might have different coefficients, the number in front? So for instance, over here, the square root of 5 down here, the 3 in front of that, we can call that kind of like a coefficient. If you remember something like this, 3x squared plus 6x minus 4. If you remember an equation like that, we're not going to deal with anything with that yet. We just say that the numbers in front of the variables and then the constant, we call those the coefficients. So over here, if I want to add 2 square roots, what I do, this thing inside the square root must be the same. I can't add the square root of 7 with the square root of 10 and anything special or magical comes out of that. That's not how it works. It's kind of like how when I had two fractions, you need the same denominator. It's going to be kind of like that for square roots. The thing inside the square root they need to line up. But once they do, I can combine them into the same square root and just add their coefficients together and slap that in front of the square root, or subtract the one coefficient from the other and slap that in front of that square root. This one might make more sense once we have some examples in front of us. So looky here, we got 7 square roots of 2 plus 5 square roots of 2. Because the thing inside the square root, because those ended up being equal, it turns out I can add them together. I basically just say I'm doing the 7 plus the 5, which is 12, and slap it in front of square root of 2. Now, why does it use that parentheses and all that? Maybe that's a little confusing. Let me state it in a way that's a little more straightforward. Let's say I have an object. The object can be an apple. The object can be an orange. It can be an aeroplane. It can be a person, although that's not really what we're talking about in this context. Or it can be the square root of 2. The object is the square root of 2. If I have 7 of an object and I add 5 of that same object together, how many total do I now have of that object? Well, 7 plus 5 is 12, so I have 12 of that object. Don't let that throw you off, because now I'm just saying I have 7 square roots of 2 plus 5 square roots of 2. The object is a square root of 2, but if I add 7 of those things with 5 of those things, I'm left with 12 of those things. I'm left with 12 square roots of 2. And that's all it is. Same over here. 2 square roots of 5 minus 6 square roots of 5. I've got 2 of this object. The object is the square root of 5. I'm subtracting 6 of that object. Now, in the real world, you don't end up with negative numbers. In reality, you can't have negative apples, but on paper we can. So I have 2 of that object minus 6 of that object. I'll end up with negative 4 of that object, or in this case, negative 4 square roots of 5. Let's look at another interesting example. Let's look at something cool here on the whiteboard. We're going to try to add 2 things, and at the get-go, they're not going to have the same thing inside the square root. But maybe with a little math-magic, we can make it happen. So let's use some math-magic. Let's say you had 17 square roots of 3, and you wanted to subtract 5 square roots of 12. Well, just keep in mind that 5 square roots of 12 means I'm taking 5 times the square root of 12 at the end of the day. Now, how many of you would say, now wait a minute, Mr. Gunther, I'm looking at that, and you told me we can only subtract these square root things from each other if there's the same number inside the square root. And sorry, Mr. Gunther, but this has a 3 on the inside, this has a 12 on the inside. How many of you would say there's nothing more we can do with that? That doesn't get any simpler than that. How many of you would argue that? Well, from my tone of voice, you can probably guess that no, I have something extra special planned for you here, and that is true. But just looking at it, you might think that, right? No, they're not the same thing. That's okay. Here's what I'm going to do. I'm going to use a little math and magic, and this doesn't always work. I've got 5 times the square root of 12. I'm going to take the square root of 12, and I'm going to call that the square root of 4 times the square root of 3. Did I break any rules there? No, you could have, now, maybe you want to go one step further. You could have said that the square root of 12 is equal to the square root of 4 times 3, and then just split that off into 2 different square roots. That's totally fine. And then we have a 5 in front, so we have a 5 in front here, and it's being multiplied. So now here's the beauty of it. By branching it off like that, what does the square root of 4 become? Just 2, exactly. Not square root of 2, even just 2. So you guys are right. Thank you, Jason. It is 2 is the correct answer. So now this becomes, well, down here, it becomes 5 times square root of 4 is 2 times square root of 3. I would go ahead and multiply this 5 times 2, and I'd end up with 10 square roots of 3. So now my original expression can be rewritten 17 square roots of 3 minus 10 square roots of, minus 10 square roots of 3. Do y'all agree with me on that? Did I break any rules? No. I don't break rules, I keep them. And now I have 17 of some object minus 10 of some object. 17 minus 10 is 7 left of that object, 7 square roots of 3. So this business over here is exactly the same as that number down there. 17 square roots of 3 minus 5 square roots of 12 is exactly equal to 7 square roots of 3. They're both going to be ugly numbers, but that's okay. Now this little trick doesn't always work. The number 12 kind of worked out for us. But if I had, oh, how about 10 square, heck, let's make it fun. Negative 10 square roots of 5 plus 31 square roots of 15. That little trick's not going to work. And that doesn't look like a 15, so. That little trick's not going to work, and that's because the 15 isn't going to simplify in some way that's really powerful enough. We could say the 15 is square root of 3 times square root of 5, but since neither of these simplify in any other way, it's not going to work. So the most succinct way, or one of the most succinct ways to write this number here is to just leave it alone and say, that's it. It's not like a fraction to where I know I can always get this a common denominator for 2 fractions I'm adding together. It doesn't quite work like that. A square root is not always guaranteed to have some kind of wonderful, lovely, simpler way of expressing it. And finally, they talk about rationalizing the denominator. Rationalizing the denominator was something we used to do, and by we, I don't actually include myself because I wasn't alive in the 70s. That's what they used to do in the 70s. And in the 70s, the problem was that when you divided by an irrational number, for instance, if I take 15 divided by square root of 6, square root of 6 is an irrational number. It turns out square root of 6, I'll give it to you exactly. Square root of 6, maybe I did it earlier, is 2.449489742783178. Ugh, that's ugly. So if I divide by the square root of 6, think about when you set up the division, you've got to divide by 2.44 blah, 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 blah. You're like, how many times does 2.44897124 go into 15? No, you don't want to do it that way. There's a little mathemagic you can do so that the number you're dividing by is just the number 2, which is a lot simpler. Where down here, this was ugly, but it turns out to not be quite as ugly as it looks. So there is a process called rationalizing the denominator. It's only necessary because old computers used to have a problem doing those computations. Nowadays, we don't quite have that problem because all our new computers, they have newer, they call them numerical methods for solving things and expressing things like that and doing those computations. So we're not going to cover it. We're not going to worry about rationalizing the denominator because it's a vestige of a lost age. Okay, so let me pull up my next set of notes, and we're just blasting through it, aren't we? We're just having a whole lot of fun. I'm going to pause the recording. There we go. Okay, back to the grind, and I bet you guys here in the room would love to see what I'm seeing. Okay, so we kind of talked about this earlier, the set of real numbers. Now we've talked about all kinds of numbers now. We've defined multiple sets. Natural numbers, those are all the whole numbers that are positive, 1, 2, 3, 4, 5, 6, 7. Then they try to say whole numbers. Don't worry about that. Ignore whole numbers. Because whole numbers, that's just like No. Whole numbers, I banish you. So we're just going to say there's natural numbers, 1, 2, 3, 4, 5, 6, 7. Then we're going to say there's the integers, which those are just the natural numbers, plus 0, plus all the negative forms of those same numbers. All of that is wrapped inside the rational numbers, which are all numbers that can be expressed as one integer divided by another. So 3/7 is a rational number. The number 5 is also rational, because you could write it as 5 over 1. It turns out that not only is it rational, it also happens to be an integer. In turn, it also happens to be whole. So the number 5 is rational. And I'm going to use the text box. Ooh. So the number 5 has a couple of designations. You can say that it's rational. You can say it's an integer. It's also a whole number. And again, we don't use the word whole, so we'll just say it's also natural. There we go. Oops. So there's a couple of different designations we can give to the number 5. What about the number -5? What are the different things we can call that? It's an integer. What else is it? Well, if it's an integer, it's in this blue box here. And anything in the blue box is automatically in this purplish box, the rational numbers. So if you're an integer, you're also rational. But the other way is not true. If you're a rational number, say -5/3, there's no guarantee you are an integer. And in fact, -5/3 is not an integer. So there's all kinds of ways we can play with these. And then the set of all rational numbers mixed together with the set of all irrational numbers, these form the real numbers, which they use this fancy R. All rational numbers mixed together with the irrational numbers, they have nothing in common, but if we put them all into the same melting pot and shook it up, that would be the the real numbers, the real numbers. So the real numbers are the ultimate large set that we're going to deal with. Let's see an example. Let's see pi. Remember pi, which is roughly 3.14159, but then it goes on forever and ever, blah, blah, blah. It doesn't have a repeating pattern. We remember that pi is one of our classic examples of a number that's irrational. It fits into this second category, but it's still a real number. -5/3, it's rational, but it's also still a real number because it's anything that's rational or irrational is going to be real. The number, how about big fat stinking 0? The number 0 0 is not a natural number. The natural numbers have to be strictly positive, 1 or greater, but 0 is an integer. 0 is rational because you could write it as 0/5 if you want. 0 is also real. So what we're going to see is that for our purposes in this course, every number we're going to run across is going to be a real number. There's no getting away from it. The way you get away from the real numbers, if you're curious, is if you've ever seen a lowercase I, which is equal to the square root of -1. That's when you could get away with it. You just said, Josh, we can't take square roots of negative numbers. You're right. So this is a special case that we're not going to deal with at the moment, at this very moment. So yeah, we've got these different types of numbers. Let's play pretend. Let's have some fun with these numbers. Let's start with the number. Oh, there we go. Let's start with the number -7. And let's not even worry about whole numbers. Just ignore that for the moment. I don't care about whole numbers. -7, what is it? Is it a natural number? No, because it's negative. So it's not natural. It's not natural. Is it an integer? Yes, so negative 7 is an integer. Is it rational? Yeah, because all integers are automatically rational. Is it a real number? Yes, because everything we're going to be working with is going to be a real number. Is it irrational? No, because remember, the irrational numbers are numbers that go on forever and ever and ever without a repeating pattern. Exactly. If you've decided something is rational, it is impossible for it to be irrational, and vice versa. If you decided something is irrational, then it's impossible for it to be rational. Oh, it's raining. I thought someone was typing really loud. It's raining outside. Yay. Everyone say yay. It looks like the 100-degree days are gone. Now, I'm native born Texan. I've lived here my entire life, and I despise the heat. I hate it with a passion. I love the cold, and I love the fall. I love the fall. Winter's great. Halloween and Christmas, that's like my favorite time of the year. You get October 1st range through December 25th. It's the best time of the year. Then December 26th is depressing. Then New Year's comes and you realize you're getting older and time keeps on slipping into the future. And you just feel like you have nothing forward to look forward to in life. That's not true. So the number negative 7 is an integer, it's rational, and it's real. Let's pick on another one. How about 0.06 with the bar on top, meaning it's 0.666666666. The sixes go on forever and ever. Is that going to be a natural number? Not on your life. A natural number is a positive whole number. Going in between two numbers like 0.66666, no, that's not going to be natural. We're not worried about whole numbers, ignore. Is it an integer? No. Integer is just the positive whole numbers, 1, 2, 3, 4, 5, 6, 7, 0, or the negative versions of them. But you can't have something that's in between. So it's not an integer. Is it rational? It is rational. Because while it does go on forever and ever, a rational number can go on forever and ever, it just has to make sure it's repeating the same pattern. If it's rational, it's automatically not irrational. So you can ignore the irrational. And then finally, all these numbers are going to be real numbers unless you try to bring in that I thing. And we're not. So 0.666666666, the sixes go on forever, is rational and real. Nothing more among those. Finally, let's look at square root of 81. Now, my brothers and sisters, you are all seeing a square root, and you might think, ooh, Mr. Gunther said square roots usually make for irrational numbers. But do they always? No. Remember, the square root of 81, it turns out that's a nice perfect square. The square root of 81 is equal to 9. So really, we're looking at the number 9 at the end of the day. 9 is natural because it's positive and it's whole. Automatically, if it's natural, it's an integer. Automatically, if it's an integer, it's rational. Automatically, if it's rational, it's a real number. And it's certainly not irrational. But you go down just a hair and you make it square root of 80, suddenly it's a different ball game. Suddenly it's a different ball. The rain. So here you go. Here's the nice chart. All the whole numbers are up there, 0 and square root of 81. We kind of did it a different way. We looked at each number at a time and classified it. So maybe we won't confuse ourselves. Now we got to look at a few kind of boring properties. Because I know so far we've talked about fractions today. We talked about multiplying and dividing fractions, adding and subtracting fractions. That stuff's exciting, huh? You guys are you're just so engaged. You're like, yeah, I love talking about that. So now this stuff is the boring stuff. So we won't spend too horribly much time here. This is interesting to a mathematician maybe, but not to just kind of if you're casually observing math. There's a few wonderful things about real numbers. If you add two real numbers, you end up with another real number. That's kind of cool. That's not true of a whole lot of other number systems that it always works out perfectly. But if I add two real numbers, the result is a real number. Why would we ever care about that? Frankly, at this level, we wouldn't. I'll just call it like it is. It's not something super interesting. Same thing for multiplying. If I multiply two real numbers, I end up with a real number at the end of it. So I can't multiply two real numbers and then get something that's complex or uses that I or anything like that. No worries there. This one's maybe a little bit more interesting. If I add some real numbers, I can add them in any order I want. I can do 13 plus 7. That's the same as 7 plus 13. Or if the real numbers are ugly, like square root of 2, square root of 5, if I add those together and I flip them, that's okay. It's the same exact thing. The commutative property, we're starting to get a little bit more interesting here. The commutative property might just be something that's useful to us. There's also a commutative property for multiplication. If I multiply any two real numbers, it doesn't matter what order I do it in. You have to be careful because your signs, you have to keep your signs in order. If you have some negative numbers thrown in there, make sure the right negative signs are attached with the right numbers. The associative property, now we're really kind of scraping the bottom of the barrel here. No, don't get me wrong, the associative property is important in math. We usually only use it to prove other mathematical principles that are a lot more interesting. But the associative property just says I can regroup things and I get the same thing. If I'm adding three numbers, I can add A and B first, then add the C, or I can do the B plus C first, put parentheses around it, and then add A to that later. It doesn't sound super interesting. It's not horribly interesting. We're talking about it. But now we go from boring, associative property of addition, boring, associative property of multiplication. You can just regroup the numbers you multiply. Boring, boring, and then ding, 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 the distributive property. Woo! Everyone say woo! Thank you. Yes, the distributive property is interesting. It is very interesting. It's interesting both because we're going to see it all the gosh darn time. It's also interesting because we're going to go backwards with it. We're going to like undo or reverse engineer distributing. We call that factoring or factoring something out. And that is something that we are absolutely going to be interested in for the rest of this course. What it says is if I'm adding two numbers together, then I multiply that entire thing by another number. I can distribute that A, I can multiply it to each of those numbers individually and then add. Wait a minute, Josh, you say. Why is that interesting or what's cool about that? It does a couple things. Let me show you a quick example of the distributive property. If I'm doing 3 times, in parentheses, 2 plus 5, well, you might just say do the 2 plus 5 first because that's what order of operations dictates, and you're right. But I can also do it like this. I can distribute the 3 and say that's equal to 3 times 2 plus 3 times 5. Could do it that way. It's going to be 6 plus 15, which is going to be 21. And you look at me and you say, Josh, that's not interesting. I don't care about that. Okay. I'm sorry for disrupting your day. No, I'm kidding. Here's where it could be interesting. Let's say you were doing 3 times the number. Oh, how about 1,157? 3 times 1,157. Maybe you can't do that in your head. Maybe you don't have a quick system for that in your head. But here's what you can do. Ooh, everyone, you can rewrite it as 3 times. Break the number 1,157 into its parts. That's going to be 3 times 1,000 plus 100 plus 50. A more clean 50 plus that 7 at the end. actually, a lot of you, when you do mental math and you multiply a large number with maybe a smaller number, a lot of us actually do it this way. Because now I can distribute. And that becomes 3 times 1,000 plus 3 times 100 plus 3 times 50 plus 3 times 7. And then it's kind of like I'm just breaking it up into smaller pieces. It's going to become 3,000, comma, Andre, plus 3 times 100 is 300, plus 3 times 50 is 150, plus 3 times 7 is 21. And while the numbers all don't perfectly line up like they did before, we can see that becomes 3,471. And it's not so bad. It's not so bad. And let me double check I did my math right. I did, okay. And yes, I am fallible. I do make math mistakes. So it becomes a little easier to digest when you can break it up like that. And the distributive property says we can break it up like that. I'm allowed to do it that way if that's the way I want it. Furthermore, we're going to see the distributive property again when we deal with variables. And now it is interesting because I can't add the 2x plus 7 on the inside there. They don't combine in any way because they're not like terms. I have to actually distribute the 3 there in order to get something maybe a little more interesting. So you got the distributive property of multiplication over addition. That might be what you call it. You have some pretty rock simple now mathematical properties. You have what is called the identity property of addition. If you add 0 to a number, whether you do it before or after, a plus 0 equals a, 0 plus a equals a. If you add 0 to a number, it leaves it alone. That's why it's called the identity, because it maintains the number's identity. So 0 then is called the identity of addition. What do you think is the identity of multiplication? Well, what's that? 1 is correct, absolutely. For addition, and we have someone down here, 1 is correct, Jason, yeah. The identity for addition is 0, but the identity for multiplication, what number can be multiplied to any other number and retain the original value? It's 1. So 1 can be deleted from a product. That's a fancy way of saying when you multiply by 1, you're not doing anything. You're just leaving it alone. That identity property is very interesting to mathematics as a whole, maybe not to us on this level, but it is something you will need to know. We're actually going to use that a lot here. Let me show you why. When we did a fraction earlier, remember we wanted to convert the fraction, I don't remember exactly what it was, I think it was 5/8. We wanted it to convert it into a fraction that was over 24 because we wanted to get the same denominator as like 11 over 12. Remember we did that earlier. The way we did it was we figured out 24 was our least common denominator, and really what we did was we multiplied the top and bottom by 3. The reason we can do that is because 3 over 3 is secretly just the number 1. It's just another expression of the number 1, because 3 divided by 3 is 1. And in doing that, while it changed the way the number looked, it didn't actually change the value of the number in truth, because all we did was multiply by the number 1, if you want to think about it. So actually, there's some real simple math tricks that help out a lot when we're solving things, equations and whatnot. Adding 0 or something that has a true value of 0, even if it doesn't look like that, that's a trick we'll use. And multiplying by 1, even if it doesn't look like it's just the number 1, it secretly is, that's another trick we'll use. And then a quick last 2 properties we'll look at, the inverse property of addition. If you have a number A and you want to find some other number to add to it to get down to the identity of 0, you just flip the sign in front of it. So for instance, if you had 3, what do you have to add to 3 to get it down to 0? You need to give it its twin, which is -3, or its twin on the other side. If I had the number negative 17, what do I need to add to that to get 0? I need to add, well, we started with negative 17. Flip the sign, I need positive 17 to do that. The reason that's going to be useful, we're going to be using that when we solve equations. If you have x plus 3 equals 4, we have plus 3 on the other side. We want to get rid of that 3 because we want x by itself. So we do that by subtracting or adding negative 3 to both sides. Same thing for the inverse property of multiplication. If you have a number, say 17, and now I want to multiply that number by something in order to get 1. We'll use that when we're solving equations also. It needs to be the reciprocal of that number, which is 1 over 17. Because remember, the original number could be thought of as 17 over 1. Or if the original number you started with was 4 over 9, what number do I need to multiply 4 over 9 by to get it equal to 1? You multiply it by its own reciprocal, which is 9 over 4. And it turns out no matter how you do it, whether you cross multiply to simplify, you could just straight up multiply, you get 36 over 36, which is just 1. So we're going to use that a heck of a lot in order to solve equations, because we need to multiply both sides of an equation by the reciprocal of something in order to get the variable by itself. Okay, I've taken attendance. Everything is set up. I'm going to stop recording.